All right, here we have a 10-meter ladder that's leaning up against a wall, and the angle that the ladder makes with the ground is 40 degrees. So off here to the left we have a diagram of the situation, and then here I just have a skinny little rectangle that we'll say is the ladder. So we're told the length of the ladder, and we're given the weight of the ladder is 350 newtons, and we're told that a 900 Newton man is 7 meters up the ladder, measured from the bottom. So the first thing we want to do is do a free body diagram that shows all the forces that are acting on the ladder. So we'll start up here in at the top of the ladder. So the ladder's leaning against the wall. So the wall is a surface, and the force of the wall on the ladder is basically a normal force. So we know that normal force is perpendicular to the surface. So the force that the wall exerts will be perpendicular to the wall. So this is force of wall right here. So we'll stick that on our diagram. So we have a force from the wall which is perpendicular to the wall, and we'll call that force of wall. All right, we're told that the man is 7 meters up the ladder, so that'll be right about here. So the man standing on the ladder, so we got this guy standing right here, he is simply a force on the ladder. And the force on the ladder is his weight, which is 900 newtons. Okay, the weight of the ladder itself goes directly in the middle of the ladder. So we'll say that this point right here is the midpoint. That looks to be about the middle. And the weight of the ladder itself is a force on the ladder. So the ladder is 350 newtons. Okay, and then the point here where the ladder is resting on the ground, there's two forces here. There's a frictional force which is preventing the ladder from slipping. So if we look here on this diagram over here, if this were a frictionless surface, then there's no way the ladder could stay at rest. The ladder would slip to the left. So there has to be a frictional force holding the ladder in place. So this force here that I'm drawing to the right is a frictional force, and friction equals mu times normal force. And remember, friction is always parallel to the surface. We learned that back in chapter 4. Okay, and then there's also a normal force. Normal force is always perpendicular to the surface. That's why we call it normal. Normal just means perpendicular. So, and remember up here, this force of wall, that's also a normal force, but we're going to call this force of wall, so that way we don't have two normal forces. So this force is force of wall, and then down here where the ladder rests on the ground, we're going to call that normal force. Okay. All right, now for purposes of summing torques, in a minute we're going to be summing torques, there needs to be a point that we define as our axis. Now the best place to put the axis is at the point where we have the most unknown forces, which in this problem is right here. So we're going to define the bottom of the ladder as the axis. Now the reason that's the nicest place is because forces that are on the axis cause no torque. And the reason for that, if you look at the torque equation, torque equals Fd. D is the lever arm, and it's measured from the axis. D is the distance from the axis to the force, perpendicular. It has to be a perpendicular distance, but it's the distance from the axis to the force. So if the force is directly on the axis, then that force causes no torque. So having the axis at this point means that the normal force and the friction force will not appear in our summing of the torques. And that's going to be a really nice thing, to be able to eliminate the normal force and the frictional force from the summing of the torques. Okay, so that's our axis, and let's go ahead and put the distances in. So from the axis up to the middle of the ladder, so we go doot, 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 doot. It's 5 meters to the middle of the ladder, to right there. It's 7 meters, so if we go from here up to the person, this is 7 meters up to there. And then the whole length of the ladder is 10 meters. So let's see. 10 meters is the distance from the axis all the way up to the top of the ladder. Okay, so let's make some room for our solution. So let's get rid of this, and we're going to shrink this down. Okay, we'll make this a little bigger. All right, so the first question is asking us to find the force of the wall on the ladder. Now, for any problem like this, what you want to do is you want to sum the forces in the x direction, which is not anything new. You did this back when you first learned Newton's laws, sum of the forces equals ma. We're going to sum the forces in the y direction, and then lastly, we're going to sum the torques. So this is going to allow us to have 3 equations for this situation. So starting with the summing of the forces, in the x direction, we have 2 forces that are x. We have friction, which is down here. It's the friction that prevents the ladder from slipping to the left. You know, the best way to understand this frictional force is, you know, if we had this ladder on a frozen lake covered in melted butter, which would be very slippery, the ladder would not stay up. It would slip to the left. So there has to be a frictional force to the right, and friction is always parallel to the surface. So friction points straight to the right. So in the x direction, we have friction, which is coefficient times normal force. That's the equation for friction. And then minus the force of the wall. Okay, sum of the forces always equals ma, but there is no acceleration in the x or the y, so this a goes to 0. So we can just change this to the sum of the forces in the x equals 0. Okay, in the y direction, so we have normal force pointing up, the normal force down here where the ladder touches the ground. Normal force is always perpendicular to the surface. Normal force minus the weight of the ladder minus the weight of the guy. And again, the sum of the forces equals ma, but there is no acceleration, so we can just change this to 0. A is 0. Okay, and then the last thing we're going to do is sum the torques. Now, the sign convention for torque, here with the forces, the sign convention I was using here is just plus, minus, you know, to the right is plus, to the left is minus, that's for the x, and then up is plus, down is minus. For torque, the sign convention is not this sign convention. The sign convention for torque is clockwise, counterclockwise. So to figure out if a force is trying to rotate the object clockwise or counterclockwise, you have to be aware of where the axis is. So our axis is down here at the bottom. That's the point where we're saying the ladder could rotate from. So this 350 Newton force here is pulling the ladder down. So if this is our axis over here, this would be a clockwise. That's CW. Same thing for the weight of the guy. This is trying to rotate the ladder clockwise. And then up here, the force of the wall is acting on the ladder in a counterclockwise fashion because it's pulling to the left. And if this is our axis, then this force is acting, the force of the wall is acting counterclockwise. So let's say that clockwise is positive, Clockwise will be positive, so these two forces are creating a positive torque, and then the force of the wall is going to be a negative torque because that's counterclockwise. All right, so starting with the weight of the ladder, so we'll start with this 350 Newton force. So the torque equation here, in fact, I'm gonna make some more room. Scoot this over. So we'll sum the torques down here so we have more room. Summing of torques takes up more space. Okay, so the torque equation that I'm going to be using, torque equals F times D, and F and D have to be perpendicular. So starting with the 350 Newton force. So there's the force, right? Force. Now the perpendicular distance for the 350 Newton force, what you do is you bring the 350 Newton force down, and then this distance here is the perpendicular distance to the force. So you extend the force, draw your perpendicular distance from the axis. D is always measured from the axis, and it has to be perpendicular. Okay, so the hypotenuse, so we're focusing on this triangle right here, and we want to solve for this distance right here, which is going to be cosine 40 times 5. The hypotenuse is 5. So this is 350 times cosine 40 times 5 meters. Okay. All right, go into the next force, or to the next torque. The 900 Newton. So we have 900 newtons, that's the force. So now what we do is we extend this down. So I'm going to clean this up here. This is getting a little messy. So we'll clean this up. Okay, that's good enough. All right, so that's our force. Again, the torque equation is force times lever arm. They have to be perpendicular. So extend the force down, the 900 Newton force, just bring it down. And then the perpendicular distance to that force is this. So now this hypotenuse, you know, this distance up the incline, or up the ladder, that's 7 meters. And this is a 40-degree angle, so this distance here, the perpendicular distance from the axis to the 900 Newton force is cosine 40 times 7 meters. The hypotenuse there is 7 meters. The guy is 7 meters up the ladder. Okay, and then on to our negative torque. So minus, now we're just going to call this force of the wall, FW. So we have force of wall. Now perpendicular distance, so now we're going to extend the force. So I'm extending this force right here, and then the perpendicular distance from the axis up to that force is this. This is the perpendicular distance to the force. So this angle up here is 40 degrees, right? If this is 40 down here, then this is 40 up here. So this lever arm for the force of the wall is going to be sine 40, or you could have used cosine of 50. Sine 40 times the length of the ladder. The hypotenuse here is the full length of the ladder. And then in this class, the torques will always cancel, which means the summation of the torques equals 0. So that is the summing of the torques. Okay, so from here, if you look at this equation from the summing of the torques, the only thing missing in here is the force of the wall. So I'm going to let you do the algebra just to make this video a little bit shorter. The force of the wall, when you solve this, comes out to be 959.361. So that is the force of the wall, the answer to the first question. And then the second question is, find the coefficient of friction between the ladder and the ground. So to get this, we first need the normal force. So you take the summing of the forces in the y, solve it for normal force, and we get 1,250 newtons. And then we take that answer and we plug it in up here. And actually we're going to take this. So we're plugging in force of wall and normal force into this summing of the forces in the x. So here we have mu. When you rearrange this, you have mu equals force of wall over normal force. And the force of the wall is 959.361. And then the normal force is 1,250, which gives us a coefficient of 0.767.